Hey, it's Mr. Allred. We're going to continue our discussion about functions, and we're up to the point of talking about implied domain. When you're given a function in algebraic terms, or as an equation, generally you're not given a graph, and it's kind of up to you to understand if the domain is all real numbers, or if you need to limit that domain to make it work. So we'll go through this. It's quite wordy in the beginning, but hopefully the examples I do will help you out. But given a function, we will always assume the domain and range are limited to real numbers. So we're trying to relate these to graphs and inputs and outputs, and our XY graph system is limited to real numbers, not imaginary, not complex. So down here, if the domain is not explicitly stated, then it's implied that we need to make sure that we take into account that we cannot evaluate function when it is undefined or give an imaginary or complex number output. Okay, let's go ahead and fix this. Evaluate a function. Alright, so finding the implied domain, up to this point there's two main problems. The first one, if, and that's an if, so that means this may not be a part of every problem you look at, but if a function has a variable in the denominator, that means x in the bottom of a fraction, then we limit the domain by saying the denominator not equal to 0, okay, and solve for the variable. So when we say not equal to 0, that means we're throwing some things away, things that it can't work. So these solutions make the function undefined and therefore are not part of the domain. Okay, so we're basically removing some things. Number two, if the function has a variable under an even root, then we limit the domain by saying the expression under the root to be greater than or equal to 0. So basically when we have a root, we want to make sure that what's under a root is positive, because we don't want those negative numbers under a root that lead to imaginary numbers. So condition 1 up here keeps us from dividing by 0. Condition 2 keeps us from taking the root of a negative number. Now, if neither one of those things happen, then for right now, for the functions we know and the operations we know, we can say that the domain is all real numbers. So those two conditions up top take us away from real numbers. So let's see what we've got here. Alright, find the implied domain. Number 1, f of x equals 7x cubed minus 4x plus 3. So thinking back to my two conditions, does it have a denominator with an x in it? The answer is no. Does it have a root? The answer is no. So the domain is simply all real numbers. Okay, no calculation needed there. It's understood. The second one here, h of x equals 12x over x minus 9. So let's ask ourselves those two questions. Does it have a denominator with an x in it? And the answer is yes. So what we're going to do is we're going to set up that denominator, which is x minus 9, not equal to 0, because we don't want the bottom to be 0. And if we solve that, we get x does not equal 9. We treat the not equals just like an equals when we solve it. So basically this means we can use any number we want except 9, and that will give us an answer back. Okay, so every other number besides 9 that we plug in we can calculate an output, but 9 makes it undefined, so we have to throw that out. Number 3, g of x equals 2 times the square root of 5x minus 3. So there is no denominator, so that's not a problem. But there is a root. So we're going to take what's under the root, which is 5x minus 3. Okay, the 2 is not under the root. and we'll make sure we set that greater than or equal to 0 because we have to have this be non-negative. Okay, we can't have a negative under that root or it goes into imaginary complex. So as we get this x by itself, we get that x is greater than or equal to 3/5, and that would be our domain. So we can use any number in this function and calculate an output as long as we put in a number that is 3/5 or greater. Okay. I'm in the way over here, so let me move. I may be frozen, it's hard to tell. But number 4, f of x equals 11 over, and in the denominator we have x squared plus 7x plus 12. Well, we ask ourselves those questions. Is there a denominator? And the answer is yes. There's not a root, so there's not 2 questions, there's just 1. So x squared plus 7x plus 12 cannot be 0. So this is a quadratic. We're going to solve it just like a quadratic. So we can factor it. X plus 3, x plus 4 does not equal 0. We would set that into 2 smaller equations. X plus 3 does not equal 0. X plus 4 does not equal 0. So the domain that we get will be x does not equal -3 and x does not equal -4. So our factoring rules and our solving rules are coming into play here. But basically in number 4, what this says is you can plug in any number you want and get an answer, except -3 and -4, which make it undefined. Number 5, g of x equals the square root of 3x plus 9, and then outside the square root is -7. So there's no denominator, but there is a root, and what's under the root is 3x plus 9, not the 7. Okay, so 3x plus 9 is going to be greater than 0. We'll solve that, and we get x to be greater than or equal to -3. So that means if we want to get a real number out, we have to plug in something that is -3 or greater. And what that also means is that when we go to graph it later on, that there will only be graph along the x-axis from -3 to the right. So we won't have graph over where x is -4 because it's not part of the input set. Number 6 here, f of x equals 7x squared minus 4. There's no denominator, there's no root. That means the domain is all real numbers. Okay? So ask yourselves those 2 questions. Is there a denominator? Is there a root? And if there's not, then you get to plug in anything you want.